Today you will see 3 ways in which one can implement a database on the Ethereum Virtual Machine, the EVM. The easiest and most used pattern in Ethereum is to have both the data and the logic or behavior that controls the data in the same contract. Another pattern is to keep the data and behavior in separate contracts and use delegate call. This is the library pattern. You can have one library being used to access and manage several data storage contracts. But there is a third one, where data and behavior are in separate contracts, but with a twist. If you know the data is immutable, you can deploy it as a contract bytecode, in the same way as you would deploy a normal contract. Then another contract or library knows how to parse and access the data by using the Xcode family of opcodes. We made comparisons between the 3 methods using the same data. The data was chosen within the EIP 170 limit, slightly below the maximum contract size limit, 24,566 bytes. All gas costs presented are only execution costs. The 21,000 base fee for transactions is not included. By far, publishing the data as a contract bytecode is the cheapest way to store immutable data on-chain, and storing it only costs 5,362,031 gas, as opposed to over 18 million for the other 2 methods. Retrieving the data is also very cheap when it is deployed as a contract, 98,000 gas cost as opposed to over 1,700,000 gas units. The difference is not obvious when you only store one slot, which is 32 bytes, but becomes of economic importance when you have more slots. Storing new data with the store opcode costs 20,000 gas units for every slot, and reading new data from storage with the sload opcode costs 2,100 gas units per slot. When you use contract bytecode for storing data, you can copy the entire data in memory in one Xcode copy instruction. Let's look at the data. I have loaded an EDS-like contract here, and we have a set named normal arbitrary. With this set, we are in the case where data and logic is in the same contract. But first, let's look at the contract on Ringby. And this is the bytecode with the data handling behavior. Let's load this normal arbitrary set. And we can see the data. This data is formed from arbitrary length rows. The last field, bytecode, does not have a static length but can be different for every row. So we can browse the data, we can see a record, we can insert, and we can update. And we can also see the field's definition. Let's go back to browsing all the sets. And the next example is this functions C set. This set references a contract that holds the data as bytecode. And we can take the address from here and look at the contract bytecode. This is the actual data, preceded by a section which describes each record length. Let's load this functions C set. And we can also browse the data, get a record, but we cannot insert nor update. The last example is the delegated contract. Let's first look at the bytecode, and the bytecode is very short because it just delegates the transactions to the code library, but it holds the data. So we can actually load it here and browse it. We see the normal arbitrary set here. So this is very similar to the first example. So we can browse the data, get a record, insert, and update the data. So you have seen the three types of storage that you can do on the Ethereum Virtual Machine. You have seen an on-chain database which keeps data on a set of contracts as linked data on EDS, the Ethereum Data Service. Our current implementation can run on the EVM and WASM. And you have seen three types of storage: on the same contract as its behavior, on different contracts, and as other contracts bytecode, which is read-only. Each contract participating in the Ethereum Data Service administers its own access control list. Storage, typing, data linking, and search are all decentralized and with homogeneous API. And this system has all the other advantages of the EDS.